A very good evening. I know it's a very long day, but I'll try my best effort to keep all of you engaging. So I'm Amrutha from BITS Pilani Hyderabad campus. The topic is AU deposited carbon thread electrode for lead ion detection in water samples. So here is the outline for the next couple of minutes. So I'll quickly go into the motivation. So from the morning to evening, there were many sensors discussed. So it's published by UNEP newspaper that 3 billion of people are at risk because they don't know the water quality. And I'm sure a couple of people are here. I'm the person who is at the risk because I don't know water quality, because I have fluorosis. After many years later, I have understood that that is because of fluorine content high in my area. And my mom has a joint pains. That is because there is a high fluorine content in my area. And being well educated, I didn't know it for years. So there is definitely a risk. So the second one is a Times of India article, like every day 7 people are being killed by water, not aware of what the water they drink. And the third one is like millions of people are at risk because they don't know the lead ion concentration in the water. And this is then the Hindu report where 75% of the rivers in India have heavy metals. Okay, there are many sensors like for lead, for fluorine, for every metal, but exactly where is the lead being get polluted? Definitely we have pollution control boards measuring our water quality, but the lead is getting contaminated into the water, especially in the pipes. You have a pollution board measuring the water quality, but the water, after measuring the water quality, is being traveled for several kilometers, at least a 10-kilometer pipeline or a 15-kilometer pipeline. So exactly the pollution is happening in the pipeline. So who is responsible to know the pollution? It's me, the user. So we all know the toxicity of lead. We know what are the problems: huge wait time, huge reaction time, and we cannot do the reaction at my home. So we definitely have to rely on a lab. And one more, water quality sensors are quite expensive. And before we want to test, we want to pre-process it with reagents. So here is the solution. Just like now we are able to measure your glucose at your home, the idea of this project is to measure your water quality at your home using your mobile phones. So first motto of this work is making a point of source device. Then the second motto is everybody are concentrating on the sensors, but at the end of the day, to test your sensor, you are again using a lab-based equipment. So we want it to be very portable, where you can measure your water quality at home. So the next idea is development of a portable potentiostat where you can connect it to your mobile phones. Then the third idea is you have to predict your water quality. Based on previous results, you can predict your water quality. So we definitely want some source where the data is stored or where we can apply some machine learning algorithms. So these three are the main mottos with which we have started this work. So again, we want the fabrication step to be very simple. The more generally, if you speak about glucometers in the market, they have an error around 15 to 20%. The more the fabrication steps, the more the error at each step you are being introduced. So we want the fabrication steps to be extremely simple. So we have a simple carbon thread. We have a gold standard solution. We do electrochemical deposition where the gold nanoparticles are deposited on the thread surface. So this is very simple fabrication procedure where you can complete the fabrication in less than 15 minutes. So here is the electrode setup which we have done for fabrication. Like this paper has been sent 4 months before. Now we have came up to a device level. Initially we tested with bulk. Now we have came up to a device level. This is the cyclic voltammetry for the gold deposition on the thread surface. So these are the parameters which we have considered after optimizing. We'll run the CV from -1 to 1 volt for 20 cycles with a scan rate of 50 millivolts. This is the optimum conditions where we found that the even deposition of the gold happened, and anything more than this or anything less than that was causing an agglomeration of gold particles. So then we have done the SEM analysis for the same. The first side is the plain carbon thread, and the second side is the AU deposited thread, where you can see very evenly coating of the gold deposited thread. So this like evenness of the gold deposited on the carbon thread will help you in repeatability and reproducibility. So this is with the lesser magnification, plain thread and AU deposited thread. So we have done the particle-based analysis where the average particle size of gold was around 558.73 mm, where the particle size ranges to 200 to 900 nanometer. So again, the EDAX analysis, the plain thread was having only the carbon and oxygen content into it. Once it is electrochemically deposited, it has gold, carbon, oxygen into it. The XPS analysis, to confirm whether the gold particles are, how much percentage of the gold particles were present. So it has carbon, oxygen, and gold into the thread surface. So the initial investigation of lead ions was, the first technique we performed was cyclic voltammetry, where we took a larger concentration of lead to see whether the sensor is really able to sense the lead. So we took a 0.1 millimolar lead ion solution, and it was showing up a very specific peak at -540 millivolt. So these are the parameters which we took. The working electrode is AU deposited carbon thread. The method of preparation is electrochemical deposition, and the potential window initially we took was from -1 to 1 volt. Then the electrolyte, regarding the supporting electrolyte, there is a specific reason why we took it as KCl HCl buffer, which is very conventional of using a phosphate buffer solution at pH 7. Maybe I'll speak about that in the next slides. And the techniques initially we used was cyclic voltammetry, and next to make it more sensitive towards the electrode surface, we went for the differential pulse voltammetry. And the scan rate for all the sensing analysis was 10 millivolt per second, and there was a very distinguished peak observed at -540 millivolt for lead ions. So for every sensor, for the calibration step, we have done the concentration analysis from 10 micromolar to 100 micromolar, where the concentration is directly proportional to the peak current. The analysis was differential pulse voltammetry analysis. Then we have calibrated it into the linear zone, where the R square value was found to be 0.98, and the linear range was 10 to 100 micromolar, which we have considered, and the limit of detection was found to be 1.57 micromolar. So to understand whether the sensor was very specific to lead and very specific to that potential, we have done interference study where the peak current was not changing because of the interfering agents. Again, the interfering agents we took were again the heavy metals which are into the water samples: copper, mercury, zinc, cadmium, nickel. So this was the thing I was saying why we have specifically used HCl, KCl electrolyte. The reaction of the heavy metal ions towards the gold deposited electrode was very specific in acidic pH. So the reaction was not happening at neutral and basic pH. So that is the specific reason where we have prepared all our samples using HCl, KCl buffer solution instead of going for PBS solution. Then we have carried out a real sample analysis with the lake water, which is very near to our campus, Shamirpet Lake Water. Initially, we have tested the lake water. The water had a very less amount of metal ions. Even we have, for confirmation, we have tested the water samples using the most traditional methods and most prominent methods, EAS and ICP. To really understand whether our senses was working, so we went into the method of serial addition, where we have added a subsequent amount of lead ions into it, and we tried to find the recovery out of it. So it was observed quite a good recovery was established around 101, 100, and 100.4 and 100.7. So these are the major things you can to conclude about my research. The technique was very simple. AU deposited carbon thread to quantification of lead ions, and the linear range we have took was 100 micromolar to 10 micromolar to 100 micromolar. Then the limit of detection was calculated to 1.57 micromolar. Then all the studies like interference, pH effect, and real sample analysis was performed. So thank you.